In the following video, we are going to address the resolution of a mock exam concerning homogeneous and composite functions, as well as free optimization, optimization without constraints, and optimization with constraints in the graphical way. So let's start here with this first exercise on homogeneous functions. So we have this function f, which is the product of x and y plus the fifth root of x to the fourth and y to some parameter beta. And the first thing is that we have to compute the value of beta so that the function is homogeneous. Okay, first of all, for a function to be homogeneous, all its terms must be of the same degree. And since we have here something which is clearly of degree 2, because it's the product of two variables, we need these to be also of degree 2. So the idea is that we want this to be of degree 2, but since there is a fifth root, the way to get, this is essentially this term as fifth root of x to the 4y to the beta. We can also write it as x to the 4/5 and y to the beta fifths. We could do it through the definition, but the important thing is that, if we have a fifth root, the interior of the root must be of degree 10, so that 10 over 5 gives us 2. And if we want x to the 4th times y to the beta to be of degree 10, of course, beta should be equal to 6, since 6 plus 4 is equal to 10. Once we have seen it without the definition, we can and we should check it through the definition. So let's do it. Now the function we have is xy, and it is quite convenient for all manipulations to put the root as a power. So it's x to the 4/5 times y to the 6/5. Now we have f of lambda x and lambda y. So lambda is the scale factor by which we resize the arguments of the function, and this is what this is lambda x times lambda y, which in this case is very easy to see that it's lambda squared xy plus lambda to the 4/5 x to the 4/5 lambda to the 6/5 y to the 6/5. And of course, since we are multiplicating powers, the exponents are added, and this is lambda to the 4/5 plus 6/5, which of course is lambda to the 10/5, which is lambda squared, x to the 4/5 y to the 6/5. So eventually we end up with lambda squared times xy plus x to the 4/5 y to the 6/5, which is the original function. So we have shown through the definition that indeed the function is homogeneous because lambda pops up in front with one exponent, and this exponent turns out to be 2. Fine. Now we must indicate by which factors should we multiply x and y, so which is the value of this lambda, so that the function gets multiplied by 16. So you see, we have that f lambda x lambda y is equal to lambda squared f of x and y, and this means that lambda squared should be 16, because this is the factor by which the function is multiplied, and this implies, of course, that lambda should be 4. Well, actually, from the mathematical point of view, it could be plus minus 4, but resizing the factors, for instance, if the function is a production function, only makes sense by positive values. Fine. Now it tells us that if this function denotes a production function, is it convenient to scale up the company? Well, it is, because if you remember, when the degree is bigger than 1, then we have increasing return to scale. So this means that once we scale the factors, the production is scaled by a bigger factor. This means that we obtain we obtain much more than what we put in a sense. So increasing returns to scale, and it is convenient to scale up the company if possible. Now, in paragraph number C, we have to verify that Euler's theorem is fulfilled for f. F is, of course, differentiable. Well, it could be some issue at the origin, 0, 0, but okay, we don't care about that, and it is homogeneous. So Euler's theorem is telling us that the gradient of the function at some point that we will denote by x is essentially a generic point xy, times the dot product with x itself should be the degree. In this case, it should be 2 times the original function. So this is 2 times xy plus x to the 4/5 y to the 6/5. Okay, so the right hand side has been tremendously easy to compute, and now we have to check explicitly that this is the case for the left hand side. So let's compute the partial derivatives. Partial derivative with respect to x is y from the first term, and now we have y to the 6/5, which is a constant with respect to x, and the derivative gives us 4/5, and if the exponent is lower by 1 unit, we get minus 1/5 here. And also the partial derivative with respect to y is very similar. Now we get x from the first term, x to the 4/5 remains constant multiplying, and then we get 6/5 times y 6/5 minus 1 gives us 1/5. So actually, what's the gradient? Okay, the gradient in this case will be well, we can actually multiply directly by x. Let's do it. It's y plus y to the 6/5 times 4/5 of x to the minus 1/5. This is multiplied by the first component of x, since it's a dot product, so we should multiply this by x, and then the second part of the gradient, which is the partial derivative with respect to y, we should multiply it by y. So in the end, we have this quantity, and now it's only a matter of simplifying. We have xy plus y to this plus 4/5 of y to the 6/5, and x to the minus 1/5 times x is x to the 4/5, plus, and you can see that now you get the same quantity, xy plus 6/5 of what? Of x to the 4/5 and y to the 6/5. So and now it's xy gives us twice xy, and 4/5 plus 6/5 is 10/5, which is 2. And this actually is giving us what we wanted to show. So we have verified Euler's theorem explicitly by computation. And now eventually we want to write, it turns out that x and y are also functions of some other variables, u and v, and now we have to compute the partial derivative with respect to u. Okay, sometimes we are asked to compute the partial derivatives alone, or sometimes we are asked to compute the gradient. The gradient of this function would be the partial derivative with respect to u and the partial derivative with respect to v, or the differential. The differential would be partial derivative with respect to u, differential of u, plus partial derivative with respect to v, the differential of v. And in this case, well, we will do it via substitution. Of course, we could use the generalized chain rule. The chain rule tells us that this partial derivative with respect to you can do it by differentiating with respect to x and x with respect to u plus the derivative with respect to y and y with respect to u. But this is usually way more involved. We will not do it this way, and 98% of the time is easier, unless you are doing symbolic computations where this is really useful. But for computations of this kind, we will just substitute. So this function of u, I mean, the letter is different just because the functional form changes when doing the substitution, but it is essentially the same function. So f of u and v is the original function f, which is xy. X is now u plus v, and now we have y is uv plus u plus v to the 4/5, and now ub to the 6/5. Okay, and let's do this derivative. First, we go with this term. This term, you can put it as u squared v plus uv squared. So the partial derivative is 2uv plus the derivative with respect to u, v squared. And now we go with the other term. The other term we can only do using the product rule. So derivative of the first term is 4/5 of u plus v. We lower 1 unit, so this gives us minus 1/5 times the second term plus the first term without deriving it times the derivative of this quantity, which is 6/5 of uv to the 1/5. We are lowering by 1 unit, but then also the derivative with respect to u of the interior, which is v. We can simplify a little bit maybe, but in this case there's no apparent huge simplification, so we can leave it as it is. And having done this, let's go with a second exercise. In the second exercise, we still are with composite functions, and then we will go to free optimization. So it gives us two functions. F is a function which takes two variables, R2, and gives us only one. And G is a function which takes two variables, x and y, and it also gives us two variables, this one and this one. So we are asked to compute the logarithm of the composition. Okay, when we write f circle g, essentially this means that we first apply of x and y. So we take two variables, then g takes these two variables, transforms it in two variables, and then we apply f to these two variables, and it gives us one real number. So my advice is to change the name of the variables that appear in the first function that we apply. So essentially, since we are applying first G, notice that we cannot do it otherwise, because if we apply the F first, then we will get just one number, and in order to apply G, we need two numbers, not one. So the other composition, GOF, wouldn't be possible. Now, instead of writing G this way, let me do something just to not to get messed, which is writing G of U and V is equal to U minus well, or let me do it how could it's okay, we can do it this way, or let me do it if we want that X and Y appear in the final result, not changing the name not changing the name to G, but doing it with F. It's the same in any case. So F of U and V is equal to what? Is equal to E to the U plus V. We have only increased the variables. And then this is what we will call U, the first variable here, and this is what we will call V. If we do the other side, the only thing is that the result will be in terms of U and V. It's the same thing. So now, U is this composite function is U turns out to be X minus Y squared. So this is X minus Y squared plus, and V, what is V? Is 2X squared plus Y squared. So to recap, the idea is that we have to first apply G to X and Y, and then we get another variables that are U and V, and to this U and V we apply F. And in order not to get messed and to apply the things to U and V, we rewrite this in terms of U and V and not in terms of X and Y. So this is the final result. Actually, it's rather simple. And we are asked to compute the log of this quantity, and the log, since we have an exponential, is X minus Y squared plus 2X squared plus Y squared. Okay, if you take this identity into account, we can maybe simplify it a little bit. Is 3x squared plus 2y squared minus 2xy. And then in B, we are asked to compute the critical points of this function. So for the critical points, we need that the gradient is 0. Partial derivative with respect to x is 6x minus 2y. The partial derivative with respect to y is 4y minus 2x. This must be 0. And the only solution to this system, you can do it by substitution, or okay, this is a homogeneous system, so one of the solutions for sure is x equals 0 and y equals 0, and the solution is unique because the two equations are independent. So x equals y equals 0. This is the only critical point, the 0, 0. Now, in order to classify the critical point, we need to compute the Hessian. And for the Hessian, let's go with the second derivative. In this case, it's 6. With respect to y, it's 4. And then the cross derivative, of course, it doesn't matter in which order you do them, because the function is differentiable. It's minus 2, so the Hessian, you can see at any point, okay, the coefficients are constant. So this is the Hessian at any point, not only at 0, 0. And now you can see that M1, the first minor is 6, which is positive, and the second minor is this determinant. 6 times 4 is 24, minus 4, which is 20. And we have both of them are positive, so the Hessian is positive definite. And what does this mean? Okay, this means that 0, 0 is a local minimum, a strict local minimum, because there's no other point that we have found to be critical. And moreover, since the Hessian, okay, we can now, in order to see whether it is global or not, okay, what can we say? Okay, we cannot, I mean, we are doing free optimization, so the domain of f, well, of h of this function, you can see this is a polynomial, is all of R2. So we cannot use Weierstrass theorem, it's not a compact set. But we can use the local global theorem because this is a convex set, the whole space, and the Hessian is for any point positive definite, so it's a convex function for any, this means that H is convex for any point in R2. And this, via the local global theorem, tells us that any local minimum should be a global minimum. So actually it is also global in this case. Remember that it's not easy in general to see whether a minimum or a maximum is global. We can try to use Weierstrass theorem or the local global theorem in some places. Sometimes you can see it from the values that take the function when it goes to infinity. There are several ways that you can see. In this case, where the Hessian is made with constant coefficients for all values of x and y, local global theorem gives us a powerful result. Okay, so now let's go with the exercise on graphical optimization. They are giving us 3 restrictions, and they are asking us to draw the feasible region. Okay, first of all, before taking into account the inequalities, let's do let's draw the curves that have to do with the equal sign. So x squared plus y squared equals 25 is clearly a circumference with a center at the point 0, 0, and radius equal to square root of 25, which is 5. So that one is rather easy. Let's do 3, 4, 5, 1, 2, 3, 4, 5, and like that. I mean, we will try to do the drawing in the best possible way. Let's see what happens. Okay, so it's this curve that goes, okay, it's not gonna be the best circumference ever, but we will try to do something that more or less tells us what's happening. So it's something like that. Okay, this is the circumference with a radius 5, centered at 0, 0. The second one is y equals to 1/2 x squared minus 1/2, which is clearly a parabola. Okay, where a is equal to 1/2, so the parabola is going this direction. It has a minimum. B is equal to 0 and C is equal to minus 1/2. The x coordinate of the vertex is then minus b divided by 2a, which is 0. So let's do a table for this parabola. When x is 0, 0, y is minus 1/2. Whenever x is plus or minus 1, Then we have that y is 0, and for instance, when it is plus or minus 2, then this is 4, 2, this is 3 halves. With this, that would be enough, but we can take some more values if we want to be more accurate. In this case, this is 9, 9 divided by 2 minus 1 divided by 2. This is 8 divided by 2, which is 4. And with this, that would be enough. Okay, actually, if we have drawn the circumference, okay, we can see that, well, some points in the circumference, for instance, are when x is valued 3 and y is valued 4 and vice versa, and with the plus and minus signs. Okay, so we can see directly without solving the system that, you see, minus 1/2 is here. Let's do the parabola. I am drawing the points where it goes, where 2 corresponds to 3 halves, and actually this point, which is also from the circumference, and it makes, okay, well, the idea is that it goes through all the points if we do it correctly. And finally, we have a straight line, which is, this is for the parabola here. And now we have eventually this straight line, which is x equal y plus 5. Okay, and we have to give 2 points whenever x is 0, y goes to minus 5, which is also a point in the circumference. And when y is 0, x goes to 5, so it's this straight line, more or less. Well, it wants to be straight. Now, to see which is the good region, let's take points. I mean, this is clearly less or equal, so it's the inner part of the circumference, it's the ball. So, I mean, if you take 0, 0, 0, 0 is clearly satisfies the inequality, so the origin, it's inside, and this means that, okay, concerning the circumference is going to this way. Now, for the parabola, for instance, if we take 0, 0, we can see that we get that 0 is less or equal than minus 1/2, which is not true. So the 0, 0, which is above the parabola, is not contained in the region. So we have to care about this part of the parabola, which is below it. And for the straight line, for instance, if we take the 0, 0, 0 is less than 5, that's okay. So we want the part that contains the region, so this part. So eventually, what do we get? Okay, we get this. Well, we take some time drawing this. It's all this region here. You can see it. Maybe it was enough that I color the boundary. Okay, but now you can see it. Concerning the boundaries, one has to be careful enough, because you see here there's a strict inequality, so it means that this boundary here is not actually contained. Okay, it's not a closed set. Okay, these other boundaries are actually part of the solution because the equality is comprised, but that's not the case for the straight line boundary. Okay, so this is eventually the region K. Now, for each of the following functions, we have to draw several level curves indicating the direction of growth, the position of the maximum, minimum, indicating whether they are global or not. Okay, first thing we should say before for any consideration is that Weierstrass theorem will not be applicable because the set K is not compact, since there's part of its boundary that doesn't K. This doesn't mean that there is no global maximum or global minimum. It only means that we cannot guarantee it. So let's go with the first function, which is x plus y. Here we have a drawing which is better than the one we have done. And you can see the level curve of value c in this case is very easy. It's x plus y equals c. It's a straight line. If we solve for y, this is minus x plus c. So all are parallel straight lines with a slope minus 1, okay? And intercepting the y-axis equal to c. So for the first one, okay, we can draw the curve. Well, we could do better. Let's see if we can do something with the straight lines. Maybe better this way. So the one that goes through here, okay, this is the level curve of value 0. Now we can do it again. The one that goes, for instance, through here. Okay, we are doing something bad. Let's see if we are able to fix it. Okay, I don't know what is happening. Let's see if we are able to do it. Okay, the one that goes this way, this is the level curve of value 2, and we can follow. You can see that the direction of growth is perpendicular, okay, and in fact, since it's a straight line, it's given by the gradient. The gradient at any point, it's always the same. Partial derivative with respect to x is 1, partial derivative with respect to y is 1. So it's a vector that goes 1 unit into the right, 1 unit upwards in the y direction, okay, for all points. So this is the direction of growth. And now, in order to see the minimum, the minima and maxima, you must see this like a front that is sweeping the region, starting from here. So the first point that you will meet, okay, is this one. Okay, you can see actually that okay, since this is perpendicular, it can be somewhat difficult to find the coordinates, but this is the you can see that the value of y is equal to the value of x here by symmetry, and since x squared plus y squared is equal to 25, then if both of them are equal, then this means that 2x squared is equal to 25, and this is x. In this case, the negative value is minus 5, the square root of 25 divided by square root of 2. So this point would be minus 5 divided by square root of 2 minus 5 divided by square root of 2. We can call it a. And then there are some other important points that you can see related somehow to the vertices. There's the point where the front kind of abandons the circumference, this region. I mean, remember that the region of interest is this one going all the way down here. Now this boundary is not included, and then there is this one. So you can see that if you continue in this way, the final point where the function within the region K has growth to its maximum is this symmetric point. That would be 5 divided by square root of 2, 5 divided by square root of 2. Okay, and now there are some other points which are important. Well, this would be clearly a global minimum because it's it's included in the region, and it's the value where the corresponding to the level curve with a lowest value, and this would be the global maximum. So the idea is that the level curves go from the lowest to the highest value following this direction. Okay. It is possible to see this the way that the level curves sweep the region here in this animation. So you can see that the level curves come here. These are the level curves of x plus y, which is the function of interest. And as we make their value bigger, I mean, this is the point where we find the global minimum. Then you can see that there's an interesting point here uh, at this vertex where we will have a local maximum. Why? Because the level curve through this point doesn't enter in the vicinity of the point, the region K. There's another point which would be interesting, which is this one, and it's quite difficult to see whether the line enters or not. Actually it doesn't, because you can see that the point where the line is really tangent is the one that we have seen that is fully symmetric. This point here. So actually in this point there's nothing, but it's quite difficult to see it from inspection. So I mean, in case we cannot see it directly, that's not an important, and it's not important as far as we make some convenient reasoning. So you can see that, and the conclusion. What's the conclusion? Is that here at this point we have nothing at all, but in this other point, which you can see that coincides with, we can call it C, which is equal to minus 3, 4. I mean, you can see that it's coordinates by inspection. Otherwise, you can solve the system among the circumference and the parabola that we had, which is y equal to 1/2 of x squared minus 1. So if you do y equals to 1/2 of x squared minus 1, then you can see that substituting, in fact, we get this point, or you can solve and get this point and this one if you solve the system. Good. So we conclude that this is a local maximum because C, the value of the function at C, is bigger than at any other point within K in its vicinity. Good. Let's go now with the other case. In this other case, the function that we must maximize and optimize in general is x minus 4 squared plus y squared. You can see directly that the level curves are of value C will be circumferences. Sorry, and this is a 4. That may seem a y. So they are circumferences with a center at the point 4, 0, and the radius equal to the square root of C. Of course, C must be bigger or equal to 0. This means that this function, as a sum of squares, cannot take negative values. What does this mean? This means that here, this point with radius 0 is the level curve of value 0. And now I will try to draw some other level curves. Okay, more or less, that would be the level curve value 1. We can try something similar for the level curve of value 2, etc. You can see that the direction of growth now depends on the point. It should be perpendicular to those circumferences. So it goes, essentially, it grows in the radial direction starting from this point, which is 4, 0. And you can make this concrete with the gradient. The gradient in this case, you can see the partial derivative with respect to x is 2x minus 4, and with respect to y is 2y. And it depends on the point, and if you substitute, you get things like that. Essentially, the level curves are circumferences that propagate from here, and now we can see what's happening in an animation as before. Now let me close this. We have another. Uh, we have put this function. I have multiplied the constant by c so that you can see faster what's happening. So essentially, when c is negative, there's no level curve. When c is 0, we have a point, and you see the level curve of different values. The function grows. So at this point, you can see that at this point there's nothing here, and well, actually we don't expect anything at 5, 0 or at 0 minus 5 because that is not included, so there's no need to discuss that. Then there is an important point you can see here in this vertex that we had computed before at 3, 4. Here we will have a local maximum because the level curve doesn't enter the region K. And if we make this grow even better values, you can see, and this is quite difficult to see a priori, that the only point where the level curve doesn't enter the region is really tangent is minus 5, 0. It's well, you can reason it. I mean, you can see that the level curve in this case is really okay. These are rowing circumferences from this point, so it's a circumference with bigger radius. I don't know how to draw this better. So at this point, what you have is the global maximum. If we go to the animation, we can see that nothing happens particular at this point because the circumference enters the region of interest. So here there is nothing, and we had seen that there is a local maximum here. I mean, when it's not clear, one can try things, but here it's not easy. I mean, one could see that the point where of this region K, which remember goes all the way to here. I mean, it's this this region here of this color. I mean, since this function grows with the distance to this point, one can think that is one of these points in this circumference, and you can try to say, okay, My circumference is like that, so y squared is 25 minus x squared. I substitute here, so now the function only depends on x, and it's x minus 4 squared plus 25 minus x squared. But when you do this and you develop this identity, the x squared go away, and you get something like minus 8x plus 16 here and 25. So something like that. When you do the derivative and equals it to 0, you get minus 8 equals to 0. It gives you nothing. And this is because in substituting the restriction, you have lost the information because of that cancellation of x squared, that x cannot take any value. It can only move from minus 5 to 5 in this region. Of course, this is telling you that the function grows linearly. So I mean, if you want this function to be a maximum, x should be as negative as possible, and it gives you this. Actually, the value of the function at minus 5, 0 is, you can see, 81. So if you were asked the image of f in this region, it would go from the global minimum, which is here. This is the least possible value of the function, which is 0, to 81. Okay, and with this analysis, we would be done. Um, Important things. I mean, there are some technicalities. Sometimes it can be difficult to really spot where the maximum is with this graphical method, uh, or the or the specific coordinates of a point. But the important thing is to argue things in a coherent way and try to see the mechanics with a simple curves like straight lines, circumferences, and parabolas.